Welcome to the Technology Addicts podcast. In this episode, we'll be diving into an article from the latest issue of Focus magazine, exploring the fascinating world of the all-electric society. Bringing intelligence to the edge. Edge computing increases the efficiency and reliability of systems in a fully electrified society. When combined with AI applications, it creates a robust and responsive infrastructure for automating power grids. In the all-electric society, data processing related to energy generation, usage, or storage is essential for maintaining grid stability and allowing customers to benefit from electrification. While cloud-based applications have been used for this purpose, they come with certain limitations. For example, a utility provider may not want the control systems for electricity supply to be hosted in data centers located outside their country. In addition, smart grids need to monitor supply and demand in real time to balance fluctuations. This requires a wide range of sensors that collect information about grid status. Additionally, processing this data in the cloud can be inefficient due to high data transport costs, excessive latency, and potential security concerns. Edge computing provides a solution to these shortcomings when needed. By implementing local computing, data storage and processing functions are brought closer to where they are needed. This decentralized approach reduces latency, enhances security, and improves system responsiveness. A utility provider, for example, can install edge servers at various points across the grid, such as substations, to process and analyze data from sensors in real time. These edge servers can match electricity demand and supply, detect faults, and manage power distribution efficiently. Edge computing can also improve grid resilience by enabling autonomous decision-making at the edge in the event of network disruptions. For instance, if a substation loses connection to the central control system, edge servers can switch to backup mode and continue operating autonomously using locally stored data. Processing data locally also helps protect sensitive information and simplifies compliance with data privacy regulations. This is particularly important in regions with strict data protection laws and ensures that utilities can meet regulatory requirements while maintaining operational efficiency. Thanks to increasingly powerful processors, AI applications can now run on edge devices. This enables faster and more informed decision-making through real-time analysis and pattern recognition directly on site. By processing data locally, companies can respond to issues immediately, optimize service processes, and improve overall efficiency. Edge AI algorithms, for example, can detect and pinpoint anomalies with high precision. An overheating power line or a transformer close to failure can be identified early and addressed before it causes widespread outages. At a higher level, machine learning algorithms analyze large volumes of voltage and current data to identify stress points in the system. With this information, operators can balance loads in real time, prevent overloads, and ensure that electricity reaches the places where it is needed most. This shift from reactive to predictive energy management drastically reduces downtime, increases reliability, and enhances grid performance. While discussions around edge computing and AI often focus on processors and algorithms, their integration also has significant implications at the component level. As computing shifts to the network edge, the increasing density of electronic components creates new challenges for power management and energy efficiency. This demands precise voltage regulation and efficient energy conversion. Modern power supply modules must therefore be compact and highly capable to meet the requirements of these decentralized systems. The miniaturization of edge computing devices also drives a need for compact, yet reliable connectors. These connectors must meet space constraints while ensuring high data transmission rates and energy efficiency. Developing connectors that combine mechanical robustness and electrical performance in a small form factor is critical for integration with edge devices. Sensors are also increasingly becoming autonomous edge devices. With integrated AI, they perform local data processing and analysis independently. These smart sensors can be used in a wide range of applications, from industrial automation to intelligent transportation systems, helping to improve efficiency, reduce latency, and enable real-time responsiveness. Edge computing and AI integration at the edge exponentially expands the potential for data utilization. This empowers a significant reduction in detection times for faults and anomalies, enabling faster resolution and reducing the risk of widespread outages. In addition, real-time information enables new services and commercial offerings to be created for end users. For example, utilities can offer dynamic pricing models or energy usage insights, enhancing the customer experience while optimizing grid performance. By bringing intelligence to the edge, energy networks become more resilient, efficient, and adaptive, paving the way for a smarter and more sustainable all-electric society. Thank you for tuning in to this episode of the Technology Addicts podcast. For more exciting episodes, be sure to follow us on your favorite podcast platform and make sure to check out the show notes.